Hey guys, welcome back. Today we're going to be talking about Ka and percent dissociation. So this will be a short one, a little bit mathy, but that's all right. So first, a bit of background stuff here. If you remember, only strong acids completely dissociate, and again, weak acids partially dissociate. And so we've been measuring up to now. We use Ka to kind of figure out how weak or how strong something is. We compare it that way. Ka can be a bit of a pain to calculate sometimes. So other than using Ka directly, often we will measure the strength of an acid by just figuring out what percentage breaks down. If it's like 99% dissociating, that's going to be a strong acid. If it's like, 1% or 0.5% dissociating, it's going to be a fairly weak acid. And so we literally just call what percent dissociates the percent dissociation. Makes sense, right? And so here's a formula down here. Keep this one handy. We're going to be using it a lot. Percent dissociation is just the concentration of hydrogen ions, which you can find either from the question, if you have the pH, if you have the Ka, you can find it pretty quick. So there's a number of different ways you can find that number, but sometimes they just give it to you. The concentration of hydronium ions. You divide that by whatever the initial concentration of your acid or base is. This, I think, pretty much has to be given to you in the question. And so they'll say, yeah, you have 0.25 molar solution of this. That's your initial concentration. So you just divide that. And then whatever the answer is, times it by 100 to turn it into a percent, because that'll give you a decimal answer. So let's look at it. Make more sense if you actually play around with it a bit. So calculate percent dissociation of a 0.75 molar solution of weak acid if I know the hydronium ion concentration is this. Okay, so I'm going to do this two different ways. Both of them will give me the same answer, but I just want to show you kind of the difference here. I'm going to show you the right way and then the kind of wrong way. So, first of all, we have some weak acid and we have H3O plus. Right? The acid is at 0.75 molar initially, which means I'm going to lose some, I'm going to gain some, and the amount I gain is 1.5 times 10 to the negative 2. All right, so this means I know that X is 1.5 times 10 to the negative 2. So I just take my 0.75 and I subtract X. So minus 1.5 times 10 to the power negative 2. And so then your percent dissociation, you just divide those two. .735 divided by 10 to the power 2 negative. Wait a second. I did that upside down, didn't I? Yeah. Always check the formula. It's your hydronium divided by your initial. Got to be careful with that one, because it's not products over reactants for the first time. Oh, it is products over reactants. Never mind. It's early. So it's still kind of products over reactants ish. And then, of course, you times it by 100 to turn it into a percent. So this is 2.04% dissociated. Now, we're dealing with weak acids here. So I'm going to show you the not as correct, but we'll pretty much give you the right answer anyways. It's a weak acid. Not a lot's going to break down, which means I can pretty much ignore that minus X. So if I want to figure out what I'm doing, I take my hydronium ion, which is given to me in the question, and I divide it by my concentration, which is given to me in the question, my initial concentration, because the amount that changes is going to be so small. So if I do 1.5 times 10 to the power negative 2, and I divide it by 0.75, I get the answer of 0.02 times it by 100 to make it into a percent. Look at that. Cheating, nasty shortcut, and it works just fine. So if you're doing weak acids, weak bases, this ignore the minus X thing will work pretty much every time. Now, technically, I probably shouldn't have done it because it's only... Actually, that's a hydronium ion. You don't even know what Ka is, so you don't know if it's a safe bet or not, because you don't know Ka or Kb, and you don't know what the acid is, so you can't even look it up. So it's, you know what I mean? It's a really sketchy to use without knowing. But the reason you can get away with it is because they said this. They said weak acid. If it's a weak acid, you are assuming, you're going off the assumption here that Ka is going to be a really small number. And so if K is a really small number, this is a safe assumption, and it'll get you through the problems a lot faster. So if you do a problem like that and you're using the shortcut and you realize you're off by like a couple decimal spots from the answer key, that's probably what it is. Maybe it was not a crazy weak acid. Maybe it was like not fully dissociated, but was like kind of moderately dissociated. We'd still call it a weak acid, but maybe it's enough that you could actually see the decimal point show up. So just be aware of that. Something to keep in mind. The shortcut will work most of the time. All right, let's look at a hard one here. Calculate Kb of the hydrogen phosphate ion. So we're going to use the hydrogen phosphate ion as a base because we need Kb. And we know the starting solution concentration, and we know the percent dissociation. Okay, well, I'm going to start where I start all my chemistry, and where you should start all your chemistry. Balanced equation. Hydrogen phosphate ion. It's going to be a base. We'll put it in water. Let's see what we get. So if it's going to be a base, it has to take a hydrogen, right? So I'm going to end up with H2PO4 1 minus plus hydroxide. All right, so there's my balanced equation. Let's get rid of this arrow. There. All right, so there's my balanced equation. 1, 1, 1, 1. Very nice. Love that. Makes things a little bit easier. What do I know? I know percent dissociation. Why don't I use that? So I'm going to look at my percent dissociation formula. So percent dissociation for a base would have hydroxide on the top instead of hydronium, but it would still have the initial on the bottom. Let's plug in what we know. I know percent dissociation. There we go. Oh, and look at that. I know it's a 0.25 molar solution. I don't know hydroxide, and that's going to be real handy to know. Because if I need to calculate Kb, what do I need to find? Well, I need this and this on the numerator, divide by this on the denominator. And this is all I got right now. So I need to find these two over here. That's what I'm looking for right now. And so I'll start with percent dissociation because, I mean, they tell me percent dissociation. I should probably use it for something. So let's give it a shot. And I can tell already by looking at this formula here, this will tell me my hydroxide. So that'll be a good first step. So 0.08. First thing I want to do is get rid of this. I'm going to divide both sides by 100. So I'm left with 0.0008 equals, I'm going to change the hydroxide to an X because that's what I'm trying to find. Times both sides by 0.25. And it turns out that X, or my hydroxide concentration, is 0.0002. All right, I'm going to write that in here. I can write this one in here too because I have it. 0.25. All right. So if this concentration is 0.0002, I mean, you could go and make an ice chart and everything to figure it out, but if you already know that's 0.002, what's this going to be? Well, it's a 1-to-1 ratio. It's got to be the same thing. The concentration of H2PO4 minus has to equal the concentration of OH minus. They both started at 0. They both came from this, and it's a 1-to-1 ratio. So I know that it's going to end up being the same number. Hey, I'm good to go. I can calculate Kb now. My dissociation constant for this base is going to be, write up the full formula for you guys. Products over reactants. Ignore water because it's a liquid. I guess I should probably write in that those are aqueous. It's just a good practice. Might as well get used to it. Liquid. All right. And I can plug in what I know. Kb equals 0.0002 times 0.0002 divided by 0.25. 0.0002 squared divided by 0.25 Kb for this weak base. Now again, wait, it doesn't even say if it's a weak base. Oh, Percent dissociation, really small. If very small, this should be a weak base. Weak base means KB should be a small number. Once I actually do the math, 1.6 times 10 to the negative 7. Yep, that's a small number. Makes sense to me. Sounds pretty good. So just to quickly recap this one here, because these ones can be a little tricky. Always start with your balanced equation. Then you can say, okay, you got to reason a little bit. I need to find KB. What do I need to find? So I probably should have started by writing up my KB formula. And I'd say, okay, well, I need to find hydroxide and H2PO4. What do I have in my question that I can use? Well, percent dissociation. So step 3, use what they give you to figure out some of your missing stuff. And if you haven't got all your missing stuff yet, that's when you have to put your thinking cap on and look, maybe I can do it with mole ratios. Maybe I can do it with an ice chart. An ice chart works just fine for this, actually. It just takes up a little more space. So if you want to ice chart it just to keep yourself organized, that'll work just fine to calculate the 0.0002. You'll find that. And then once you've got all your numbers figured out, finally you do that final calculation there. But that's actually it for today's lesson. It's pretty short, pretty sweet, but that's percent dissociation in a nutshell. Thanks for watching, guys, and I'll see you next time.